Hi folks, this video is on the metalogical theorem called truth functional completeness and the TFC algorithm that goes along with it. Truth functional completeness is the following idea. It's a characteristic of formal systems, and take any possible truth function. That's an arrangement of truth values like TFFF, that's the truth function for conjunction. It's an arrangement of truth values from a truth table. If I give you some random truth function, like an 8-row truth table with 4 T's and 4 F's, or a 32-row truth table, are we sure that a certain logical system can express that truth function? What about the Boolean connectives? Can they express any possible truth function? That's what truth functional completeness says. If I take a system like bool or prop, any truth function that's logically possible, my system is able to express. Here's an example. Here's an 8-row truth function. I'm taking the inputs to be P, Q, and R, and I've just arranged a random array of T's and F's. How do I know that bool or prop can write a sentence up here such that if we computed the truth function of that sentence, it would give me this exact truth function? Well, if there's a set of connectives like the Boolean connectives or the propositional connectives that can do that, then they count as truth functionally complete. Pause your videos now and see if you can give me such a sentence. You learned how to do this using the TFC algorithm in the textbook. Okay, that was your chance to pause your videos. If you need multiple choice, you can check these to see if any of these is the correct answer, but I think you're able to do it even without the examples. Let's see how the TFC algorithm works. Step 1 says, just focus on the rows that are T. You could ignore all the other rows. All that matter are the T's. And for each one of those T's, here's step 2, we form a conjunction. And how do you know what to put in the conjunction? Just look over here at the reference columns. If this atomic sentence is true, you put it in. If the atomic sentence is false, like Q on row 4, you put the negation in. And here's my conjunctions for those 3. Now, the last step of the TFC algorithm says, let's just disjoin all of those conjunctions. Let's put a disjunction between each of them. Now we have this big, long, complex sentence. It looks like this. And notice what happens. If you compute the truth function of this thing, you know what you're going to get? You're going to get this exact sentence. Because when is this sentence in blue going to be true? Well, this conjunction here is true just on one row. P, Q, and R all have to be true in order. That's how AND works. All of these have to be true. So this blue one is true just on this row, and this blue one is true on just this row. In a sense, what each of these big conjunctions says is I'm on row 1, or I'm on row 4, I'm on row 5. Now, if we disjoin those things, what the sentence says is either I'm on row 1 or 4 or 5. This is going to be true just in case we're on one of those rows, and it's going to be false otherwise, which is indeed the exact truth function that we were looking for. Now, notice the algorithmic procedure that I gave you is completely general. It can apply to any possible truth function. It doesn't matter if it has 2, 4, 8, 16, 32 rows. It works no matter how big the truth function is. So what that shows is that the Boolean connectives can express any possible truth function. So indeed, the Boolean connectives are TFC, or truth functionally complete. Now, you can remember those De Morgan's laws. They're not the only sets of connectives that are complete. Actually, there's a really nifty proof that you only need 2 of the Boolean connectives. Negation and conjunction alone are good enough, or negation and disjunction. How could we do that? Well, first, all we have to do is add to our algorithm, because the first procedure shows you how to express any possible truth function with the Boolean connectives. What you can then do is find any disjunction. Anytime you have a disjunction, like in those other examples, then what we do is we replace that disjunction with this totally messy thing using De Morgan's law and double negation. Now, this looks way messier, but notice it just has conjunction and negations in it. So that means that conjunction and negation alone are going to be truth functionally complete. But there's nothing special about conjunction here. You can do the same thing with disjunction. So really, you only need 2 of those connectives. But that doesn't mean any 2 connectives work. If I give you conjunction and disjunction, that is not going to be truth functionally complete. There's problems with that. And in the textbook, we talk about exactly why that's so. What are the counterexamples? It turns out negation and the biconditional are also not complete. But if you remember, the negation, the disjunction and the conditional, remember, are sort of interchangeable. If you remember to negate the antecedent. So actually, there's an easy proof that negation and the arrow are truth functionally complete as well. But notice, all of those examples require negation. Negation alone is not good enough. It has its own problems. For one thing, it can only express an even number of T's and F's because either it's going to keep flipping values when you keep adding negations. It also has a syntactic limitation because it only has one input. So there's other limitations to negation. So that would raise the question, if none of these Boolean connectives is truth functionally complete alone, is there any connective that's truth functionally complete alone? It turns out none of the ones in our language of prop or bool can do the trick, but that doesn't mean there is none. So we'll look at some other connectives in some other videos. Thanks.